Despite its northern location, Europe enjoys a remarkably mild climate. Winters in London are far warmer than those experienced in cities at similar latitudes in Canada. Coastal Norway remains navigable year-round, despite being located astonishingly far north. This climatic advantage has helped shape European civilization for centuries. It has influenced agriculture, trade, population growth, and economic development. But there is growing concern among scientists that this advantage may not last forever. The reason Europe remains relatively warm lies largely in the Atlantic Ocean. More specifically, it depends on one of the most important systems of ocean circulation on Earth, the Atlantic Meridional Overturning Circulation, better known as the AMOC. While most people have never heard of it, the AMOC plays a critical role in regulating temperatures across vast portions of the globe. Without it, Europe would look very different. This system functions like a gigantic conveyor belt moving water through the Atlantic Ocean. Warm surface water flows northward from the tropics toward Europe. Along the way, it transports enormous amounts of heat. As this water reaches the colder regions near Greenland and the Arctic, it begins to cool. Evaporation and sea ice formation leave behind higher concentrations of salt, making the water denser. Eventually, this cold and salty water becomes heavy enough to sink thousands of meters below the ocean surface. Once submerged, it begins a long journey southward toward Antarctica. Far to the south, powerful winds and ocean processes gradually pull this deep water back toward the surface. It then begins another journey, eventually returning northward through surface currents that connect with the Gulf Stream. The cycle repeats endlessly, transferring heat from tropical regions toward northern Europe while helping regulate global climate patterns. The scale of this system is difficult to comprehend. Individual water molecules can spend hundreds or even thousands of years completing a full circuit. Despite this slow movement, the AMOC continuously redistributes heat around the planet. It also transports nutrients that support marine ecosystems and fisheries throughout the Atlantic. In many ways, it is one of the hidden engines that helps sustain life and economic activity across large portions of the world. For Europe, the impact is especially significant. Warm Atlantic waters, moderate temperatures across the British Isles, Scandinavia, northern France, and other regions. Without this constant supply of heat, much of northwestern Europe would experience winters more similar to those found in Labrador, Quebec, or northern Canada. The troubling possibility now being discussed by climate scientists is that this system may be weakening. Some researchers fear that if current trends continue, the AMOC could eventually reach a tipping point beyond which recovery would become extremely difficult. If that were to happen, Europe could experience profound climatic changes unlike anything seen in modern history. Popular culture introduced many people to this concept through the 2004 disaster film, The Day After Tomorrow. In the movie, a collapse of ocean circulation triggers a sudden global ice age that engulfs major cities within days. While that scenario is scientifically unrealistic, it was inspired by genuine concerns regarding ocean circulation and climate stability. The real-world consequences would unfold much more slowly, but they could still be severe. One of the major concerns involves Greenland. As global temperatures rise, the Greenland ice sheet continues to melt at an accelerating rate. This melting releases enormous quantities of fresh water into the North Atlantic. Freshwater is less dense than salty seawater, and as more of it enters the ocean, salinity levels decline. At the same time, ocean temperatures are rising. Warmer water is also less dense than colder water. Together, these changes make it increasingly difficult for water near Greenland to sink and drive the deep water formation process that powers the AMOC. This creates a dangerous feedback loop. Less sinking water weakens the circulation. A weaker circulation transports less salty water northward. Reduced salinity makes sinking even harder. The cycle can gradually reinforce itself over time. Scientists worry that beyond a certain threshold, the system may become unstable. Once crossed, recovery might take centuries or even millennia. Because the AMOC operates on extremely long timescales, restarting it after a shutdown would not be a simple matter. Even if humanity dramatically reduced greenhouse gas emissions, the ocean system itself would require generations to recover. Concerns about the AMOC are not new. Researchers have been studying the possibility of its weakening for decades. Early theories emerged in the 20th century, but limited data made it difficult to draw firm conclusions. That changed in the early 21st century with the development of sophisticated monitoring networks spanning the Atlantic Ocean. One of the most important projects is known as RAPID, a vast array of scientific instruments stretching across the Atlantic. These instruments continuously measure ocean currents, temperatures, pressure, and other critical variables. Together with additional observation systems operating in different regions, scientists now possess an unprecedented ability to monitor changes in ocean circulation. The data collected over recent decades has raised concerns. Measurements suggest that the AMOC may already be weakening compared with earlier observations. While the exact magnitude remains debated, multiple studies indicate a downward trend. Researchers continue analyzing whether this decline represents a long-term shift driven by climate change or a temporary fluctuation within natural variability. Determining the answer is not easy. Ocean systems are enormously complex. 20 years of direct observations may sound substantial, but in climate science, it remains a relatively short period. Researchers must distinguish between long-term trends and natural cycles that can span decades. However, there is an important clue from Earth's past. Scientists know that large disruptions to ocean circulation have occurred before. Near the end of the last ice age, approximately 12,000 years ago, vast ice sheets covering North America and Europe began melting rapidly. Huge volumes of fresh water poured into the North Atlantic. The resulting reduction in salinity weakened ocean circulation and triggered a dramatic climatic event known as the Younger Dryas. Temperatures across parts of Europe and North America dropped sharply. Greenland experienced even more dramatic cooling. These changes unfolded over decades rather than centuries, demonstrating that major climate shifts can occur surprisingly quickly when critical thresholds are crossed. The Younger Dryas lasted for roughly 1,000 years before circulation patterns eventually recovered. It remains one of the strongest examples that large-scale ocean circulation changes can dramatically alter regional climates. Today, scientists are searching for signs that similar processes may be developing once again. One frequently cited piece of evidence is a region of unusually cool ocean temperatures south of Greenland. While most of the world's oceans have warmed over the past century, this area has remained comparatively cool. Some researchers interpret this anomaly as a possible signal of weakening circulation. The scientific debate, however, remains intense. The Intergovernmental Panel on Climate Change currently assesses that the AMOC is likely to weaken during the 21st century. At the same time, it considers a complete collapse before 2100 unlikely. Under current projections, the system is expected to lose a significant portion of its strength, but remain operational. Not all scientists agree. Some argue that existing climate models underestimate the risks because they do not fully capture the effects of Greenland's accelerating ice loss. Simulating ocean circulation requires enormous computing power. And even the most advanced models must simplify certain processes. As a result, different studies produce very different timelines. Some suggest a collapse remains centuries away. Others propose that under certain conditions, major disruptions could occur much sooner. The uncertainty itself has become part of the concern. When dealing with systems that influence the climate of entire continents, uncertainty does not necessarily imply safety. Several prominent oceanographers who once considered a collapse highly unlikely have become more cautious in recent years. As evidence accumulates, some now argue that the probability is substantially higher than previously believed. Governments are beginning to pay attention. Countries located around the North Atlantic have a particular interest because they stand to experience some of the largest consequences. In recent years, discussions about the AMOC have increasingly moved beyond scientific conferences and into national security planning. What would happen if the circulation weakened dramatically or collapsed altogether? The most immediate effect would likely be a major cooling of northwestern Europe during winter. Despite ongoing global warming, the loss of oceanic heat transport could overwhelm regional temperature increases in certain areas. Winter conditions across parts of Britain, Ireland, Scandinavia, and Northern Europe could become considerably harsher. Sea ice would expand across areas that remain largely ice-free today. Portions of the North Sea and Baltic Sea could experience much greater seasonal ice coverage. Maritime transportation would face new challenges, requiring larger icebreaker fleets and more resilient infrastructure. Cities that currently experience relatively mild winters could see far colder conditions. Extreme cold events would become more frequent. Energy demand for heating would rise substantially, placing greater pressure on power systems and infrastructure. Agriculture could also suffer. Changes in precipitation patterns may reduce rainfall across portions of northwestern Europe. Some regions could become significantly drier, making traditional farming methods more difficult. Food production could decline while costs increase. At the same time, summers might not cool nearly as much as winters. This would create larger seasonal temperature contrasts, producing climate patterns that resemble parts of continental Siberia more than modern Western Europe. Southern Europe would face a different challenge. While northern regions cool, southern regions would likely continue warming. Drought conditions could intensify, placing additional pressure on water supplies, agriculture, and ecosystems. The consequences would not stop at Europe. A weakened AMOC would affect weather systems around the world. Changes in rainfall could influence the Amazon rainforest, African drought patterns, and Asian monsoons. Rising temperatures around Antarctica could accelerate ice loss and contribute further to sea level rise. Along the eastern coast of North America, sea levels could increase faster than the global average because of changes in ocean circulation. Coastal cities would face additional flood risks on top of those already associated with climate change. None of these outcomes would happen overnight. The world portrayed in disaster movies is fiction. There would be no instant ice age and no walls of frozen air sweeping across continents within days. But the real consequences could still be profound. A gradual weakening of the AMOC would reshape weather patterns, economies, ecosystems, and societies over generations. The greatest concern among many researchers is not necessarily what happens tomorrow, next year, or even next decade. It is the possibility that actions taken during the 21st century could push the system beyond a tipping point, committing future generations to centuries of consequences that cannot easily be reversed. For now, the AMOC continues to flow. Europe remains warmer than its latitude suggests it should be. Ships continue crossing ice-free waters, farms continue producing crops, and millions of people continue living within a climate made possible by one of Earth's most remarkable natural systems. The question scientists are racing to answer is whether that stability will endure or whether future generations will look back at this period as the moment when one of the planet's most important climate regulators began its irreversible decline.